Hello guys, welcome to another episode of Xahlee Talk Show. So we're gonna do geometric inversion again, mathematics and geometry. Lots of code. So Wolfram language, mathematics, geometry, and I'm just gonna go random, okay? So if you have questions, post it. If you are watching this offline, play at 1.5 speed. Okay, let's go to today's talk show. So let me double check, voice check. This is perfect volume. Yes. Video check. Am I good to go? Yes. It's kind of chaotic here. Okay, let me put this up a little bit. Okay, so my mouse, my keyboard, the keyboard is Glove 80. This one, fantastic. This is Ultimate Hacking Keyboard 2, fantastic. I have a video review on my website, on YouTube, if you search for it, and this is Svalbard, SVALBOARD, fantastic. Okay, video review on YouTube. So what we're gonna do is I got lots of things to do. I'm going to demo a Wolfram language package. Okay, so Wolfram language package, geometric inversion, that's what we're gonna talk about. So this is geometry. I talked about it multiple times in the past year or two. So go to YouTube, search for it. Okay, so there are several things I need to do. I'm wondering, so anyone here? Hello, Dan. So what do you guys like to see? Like, I can do a full tutorial, kind of explain this geometric inversion. So it's a mathematics lesson, but I've done that many times in the past. And I just gonna do random, okay? Because what I mean by random, because I have a lot of things to do working on my website. Let me show you, random, like what I've been working on in the past hour. For example, this is GeoGebra. This demonstrates that let's see if I can move the curve. Okay, so let's demonstrate that if you have a wait, why does it go to the other way? This is so refresh. So this is a curve, of course. Well, anyway, this demonstrates that if you have a bunch of circles where the centers of the circles all lie on the line, like a bunch of circles, horizontal circles, then if you let's see, if you oh God, this is about the curve tractrix. Okay, that's a blue line. That's a line you get. That's basically the trail of a bicycle. So if you have a bicycle and you go straight, but you turn your handlebar, so you make a turn, then the hind wheel will trace out this curve. Okay, so that is about the tractrix. Anyway, that's about that curve. Okay, so I'm kind of like going random, no focus right now. Did you major in math or in computer science? Well, I went to community college for 3 years, but I never got any degree. Okay. So I studied mostly mathematics in college. In the community college. Basically, that's the first 2 years of college. But mostly, I do programming. Okay, so I learned programming mostly by myself. Okay, there's a bunch of curves. So you can see this is a visual dictionary of special plane curves. Lots of, because I got so many of them open right now because I was working on them on the GeoGebra thing. Okay, I'm kind of confused right now. So let me focus, okay? There are a few things I want to do. So first of all, Wolfram language, have I demonstrated yet? Okay, so let's show Wolfram language. Let me show some Wolfram language, okay? So did it start yet? Okay, so let's start it again, okay? Click on that. Fantastic, Wolfram language. Now you can get it for free. So let's magnify 3, Shift Enter to evaluate it, and magnify so it's easy to see, and show today's talk show. I want to show, so we did this, I think each one of them live streamed it. So for example, you can copy that code, paste it here. So that's a code. Shift Enter to run it. So you got grid, and after the geometric inversion transformation, it became that. Okay, that is that. So that's one example. Then there's other variations. We did this coding live sometimes in 2023. Let's show some others. So this one is one of the graphics I created, I'm most proud of. So let's it too big. So here's a code, about 30 lines of code. Shift Enter to evaluate it. So first of all, you draw a bunch of grids, then you apply the geometric inversion. So you got this like still two-dimensional. Then all you have to do is you add a dimension to it, then you got this beautiful tile. Okay, this is the most beautiful. And so this is a geometric inversion of a grid. You begin with the grid. But however, here's the extra. Okay, so here is the extra. So what you don't want is that, you see, when you apply geometric inversion to a bunch of grid, you got this center, which is a lot of, let's see if I can like magnify the center or something. So click on that, shift, no, control, no, control shift, no, shift, click, oh yeah, so you can enlarge. So you see, the closer, wait, so the closer they are to the center, they became more crowded, okay? But if you want this as a garden tile, you don't want that because they become infinitely small. So what you do is you find a way to, the final result is that you don't want them to be crowded in the middle. So what you do is, first of all, you create this image on the left. So they become super crowded in the middle. Then after you invert, then they became equally distanced like that. So it's a beautiful image. So I'm pretty proud of this design. You have to do some thinking to create this. So here's a code, Shift Enter. So you see, first of all, we create this image, which is super crowded in the middle. Now, why is it not scalable? Well, it is. Okay. So you see, then you apply the inversion, then you get that. Then you add a dimension. You make it three-dimensional. So here is a whole three-dimensional code. There it is, about 100 lines. Shift Enter. So there's one, there's that, there is three-dimensional image, and this is the final result. Beautiful. So you can put this in your backyard as a tiles of a garden. You see, you can see the pattern of a circle there, many circles there. So anyway, I'm kind of going over. then inversion is always fascinating. Yes, video, audio. Okay, I'm kind of going all over. What is it I want to do? So I wanted to. So that's some like fancy demonstration of geometric inversion, and this one is inversion of a three-dimensional lattice. Like grid lines. So let's paste it. Very simple code. So you can see you create this kind of image. You begin with the grid, of course. So this one, I think. So let's try that. Paste, run it. So you begin. So this one is like a fancy grid. Okay. Then you have the simpler grid. Then you have another variation. This is a grid without, without the edges, kind of cube without the edges, but with the cross center lines. And then you have another variation. Then here is their inversion. So you can see there. Fantastic. Okay, so I just wanted to show some demo of the inversion so that so it gets you interested in this geometry and the Wolfram language. Okay, so you can download it for free on this link. Download Wolfram engine and turn on JavaScript. Okay, so you can find my link. Just search for xahlee Wolfram language for programmers, xahlee.info. Okay, and here is a download link, and you also just read about them. So it explains what's the difference between Wolfram language, Mathematica, Wolfram engine, and Wolfram script. Then you also want to download the Wolfram, the Jupyter notebook. So that way you can get graphics. Okay, you have graphics, or you just pay for Wolfram language. You pay for them. Okay, so that's just intro. There's many things I need to do. Okay, so but it's hot. Hello, Tamid. Okay, so what is the next I want to do? Yeah, so let's go. Let's go to the directory. So I got a bunch of to-dos. That's Emacs. So here is change of the syntax. This code. Here is So I want to change some syntax and stuff. Okay, so this one I want to redo and using SVG. Okay, and here is change the file name. Okay, so let's do them. Okay, so this is just gonna be my work session then. Okay, so if you have questions, ask me. Okay, otherwise it's just me working on this. So inversion of a line. So all these are a bunch of GeoGebra applications. This is an inversion of a line. So that shows, let's see. So this blue line, the inversion of the blue line is the red circle. So you can see there. Now, let's change the title there. So all these, let's add the GeoGebra title there. Okay, do it. That's done. Go back here, refresh. Okay, that's good. So here's the index of all GeoGebra files. Okay, so okay, inversion. So I need to rename that. So Okay, so here is a file. I want to rename this, so instead of just inversion, it should say geometric inversion. Okay, so I got a command. You can see in the pink window, press. Okay, so this should be geometric. Do I have that? No. Okay, do it. It'll go through my 7,000 files and find the appropriate links and change them all. So it's all changed. Okay, so that is done. Delete it. So you can see, if you refresh, you can see, and you go through that page, you can also see. So this page shows the most basic definition of geometric inversion, which is, so given a point P, it becomes this point Q. So if P is smaller, Q becomes larger. If P is smaller, Q becomes if P is larger, Q becomes smaller. So this geometric inversion is just like 1 over X. Okay, so this rename is done. Let's go here. So that page, I need SVG. There's a lot to do here because I need to write a Wolfram language code that converts to SVG. Wolfram language can do it, but however, it's got some issue. So let me demo. Okay, so let's demo this one, geometric inversion of a regular polygon. Okay, so close that. So this is the Jupyter Notebook. Close that. So this is download. Close that. And here is, let's see, where is that? That's somewhere here, I believe. No, here. Okay, so you can apply geometric inversion to this bunch of octagons. Let's see, 1, 2, 3, 4, 5, 6, 7, 8. So each one of them is an octagon. When you lay them on a grid, you got this pattern, kind of beautiful. Then you apply the geometric inversion to them. Then it becomes this pattern. Okay, so here's a code. You can copy it and paste it and Shift Control T to make it typeset. Okay, I don't want this form. Shift Control N. Wait, why is kind of very too large. Okay, so I mean, I'll leave it. Okay, Shift Enter to run it. So there it is, and there it is. Okay, so what is it I want to do? Yeah, so I want to demonstrate export to SVG. Okay, so this is kind of too large. Wait. So Shift Control and Shift Control I to turn it into input form. Shift Control N. Okay, so what I want to do is, if you run this, you get this picture. You can export it to, this is GR1. So for example, GR1, Shift Enter. So that's the output. Then you can say export. Okay, export GR1. Then you just say SVG, something like that. Yeah, a name. So wait, the name first. So you say octagons SVG. Octagons SVG. Then you say GR1. Okay, I believe that's a syntax. Shift Enter to run it. Okay, it's done. Let's look at the documentation. Yeah, file name first and the expression. So now we go to download. Wait, document, I believe. Then search for octagon. There it is. So that's a SVG file. So open it. In Emacs it shows it. but now you can go switch to xahlee mod, which also works for XML files. SVG files are just XML. So you can see the file size is 88 kilobytes. Okay. Now if you copy it, go to today's talk show, and let's paste it somewhere here. What is this? Okay, so let's make it. So paste it, that, make a link. Okay, it become, then let's move this into talk show. Okay, so I call a command xahlee rename file. Wait, not that, xahlee rename xahlee move, cancel. Okay, now do it. Press xahlee move source file path into talk show page. Okay, then you can see it's there. Close it, show in browser, go to the bottom, there it is, the SVG. So you can export SVG, but however there's a problem. Now if the image contains a circle, it doesn't export them in the SVG native circle. Instead of, it creates a bunch of lines to emulate the circle. So the result is that the file size is gonna be unnecessarily 10 times larger. Can we show an example? Yeah, sure. So okay. So let's, okay, yeah, I need to do this anyway. So let's do a Wolfram language. I'm using xahlee Wolfram mod. If you are using Emacs, you can search for it. You'll find it, okay? So here is xahlee Wolfram mod. Go to the source code, go to the top, go to the URL, open it, show in browser, search for that, you'll find it, and it's available on GitHub. Okay, so close that. Now let's do circle. Okay, circle, you need a center 0, 0, and you need a radius 1. Okay, now that's a graphics. Let's say XX equals to that. And now let's say export. Export, yes, and circle. Okay, name it circle SVG and XX. In fact, we can just put the XX, that expression. Okay, now if I run it, it'll export this SVG. Okay, now run it, do it. Okay, refresh, search for circle. Wait, where did it go? It went to what? Where did the file go? Wrote I don't, where did the saved SVG? So because let's do it again. Okay, so wait, let's go to download. Okay, refresh. Wait, not download. Let's go to documents. Refresh. Search for CIR. Okay, it's not there. So where is it? So, okay, it's saved in the current directory. So there it is. Okay, open that. So that's SVG. Okay, this is incorrect. It actually just kind of screenshot the expression. Okay, so let me show you. Copy the file path, close it, put it back, and put that there. Linkify it, show in browser, go down. So you can see it actually kind of just screenshot that text. That's not what we want because I forgot something. So open it, delete it, remove this image link, and go back to this expression, pop it out, and so what's missing is that here this circle needs to be a graphics object. So all we have to do graphics, okay, then put that inside, okay, then that's what you want, okay, there. Then you evaluate this file. Done. Here's your result. Go to the directory. There it is. Copy the file path. Well, open it first. Then you can see a circle. Now make it xahlee mod. Press. Then we can see. Now we can see the source code. So you can see it's one single line of path. So let's make it. You see. So what this demonstrates is that when you export a graphics that contains a circle, it doesn't use the SVG's native circle primitive. Instead, it uses SVG path. So you got this whole bunch of points to emulate the circle. Okay, so do you guys know what I'm saying? Am I doing well? So the question, what's the basic idea behind inversion in general? Okay, let me explain that. But I explained that so many times in my several videos. Just search for inversion on xahlee YouTube. But I'm gonna explain that. Okay, so anyway, the SVG. So if you don't know, search for SVG tutorial on xahlee.info. You'll find it. So SVG is just a XML file. So here is the most simplest SVG, XML, just like HTML. So if you put this in a browser, you're gonna get that line. And here is a complete source code. So if you say rec something x9, y0 with height, and style, field, green, stroke, blue, something, you get rectangle, okay? So this SVG stands for scalable vector graphics. Very simple. It's just like HTML, okay? But they have, but you have a bunch of primitives. You know, you have rectangle, you have line, rectangle, rect. Then you can make it round corner by using, you know, the attribute rx, ry. And you have a circle primitive, circle, you can see, with cx, cy for center and r for radius. So that is one of the primitive of a circle. And here is in combination with JavaScript, so you can kind of draw an arc, move up and down, and you can, let's say, start angle and sweep angle. And what is this? Yeah, you can change arc and you can change rotation, and you can do a elliptical art here, which is, you know, change the ellipse, change that major radius, circle arc. So there is another application. Where is it? Anyway, so that's the basics of SVG. But the issue here is that when you export a circle, it doesn't use the circle primitive. So if it does, then, oh God, I kind of, explaining all these things, which I did before. So let's paste the link. So the issue is that if you don't use the circle, then you're gonna have lots of, the file size is gonna be huge. Now where is this one? Octagon documents. Wait. Okay, close it. Now go back here. So you see, the problem is it uses this path primitive, so it creates lots of numbers in between. But in fact, you just need center and radius. So you need to write a code to export yourself. Basically, you want to turn a Wolfram language graphics like, like this line. This line is a graphics. So you want to turn that. So basically, you want to write a program that turns this expression into a string, SVG string. Can we do that? Yes, that's what I have to do. Okay. So you need to write a function. Let's say export SVG. Let's say Wolfram language does not allow dash or underscore. So you need to define a function. So basically, what we can do is something like that. Okay. So then you take an expression that basically returns a string that is this SVG. But to write that, let's make this HTML. To write that, it's gonna be a bit involved. I mean, that's gonna take. It's going to take like half an hour. Because actually let's rename this to SVG string. Okay, so SVG. Okay, and basically return a string. Return a string of SVG code that represents the expression. Okay, the expression expr here. Okay, that's a function I need to write. Why do I need to write that? Because in my work, I have huge amount of Wolfram language graphics that requires a circle. For example, this is sine curve, and I want to export to SVG instead of bitmapped graphics. Why? All these are right now bitmapped graphics. Why do I want SVG? Because bitmapped graphics are not scalable. So for example, open this image, go to that, and enlarge. As you can see, the more you enlarge, they become more ugly. They become jagged. You see? But with SVG, this doesn't happen. You can enlarge however large you want. And you can see that if you, I have a lot of articles. Okay, let me explain that, shall we? Okay, so go to, let's open that. Okay, start search. SVG, just type SVG. And you can see 38 articles about SVG. And one of them is, so there's a lot of talk shows in the past about SVG. And one of them is, so you search SVG and let's see, there it is, Canvas versus SVG. Open that. Canvas is another technology for two-dimensional graphics on the web. Okay, so you can see here is a difference between Canvas and SVG. So here is a canvas. Now let's enlarge the page. So you can see Canvas remains fuzzy if you enlarge it. You see, but the SVG is very sharp. So that's the difference. That's a major difference. Canvas is a bitmapped technology created by Apple around 2008 or so. It's not good. Well, it's suitable for video games. So which is the biggest market, if you do video games, if you sell video games, most people play video games, especially on the phone, then you use Canvas. Okay, but otherwise, SVG is a kind of much better technology if you need illustrations and all that. So that is why, because my website, mathematics, there's a lot of illustrations. So I want them in SVG. So what I can do is to, so where's my page? Okay, so what I can do is, use Wolfram language to generate all this code easily and this animation, for example, then export them to SVG so that on the web it remains beautiful. And the file size is very small. For example, right now, this is a MP4 video file, fairly large. So that is the reason I want to use SVG, but I need to write this function, okay? So how do you do that? I can do that. I can kind of start to show you how to write that program, but that would be kind of advanced Wolfram language coding. It's not too difficult though. So first of all, we need to let me show you the basics. Okay, clear. So you want to clear that first, then you want to define it using this way. I'm not gonna explain why, but so what is the expression you want? Yeah, let's just say something graphics. Okay, then you just basically return a string. And the first part of the string is going to be, let's quote this, okay? So escape quotes, so they become kind of, they become a string. So you need to copy the whole thing, cut it, make it a string, paste. Now they become a string. Well, except there's still something that's you see, you run into the escape sequence issue. So, oh yeah, so that so what is so right now, so this is Wolfram language. Right now we are in Wolfram language, okay? So this whole thing needs to be a string, and but beginning here something went wrong. Wolfram language string is very similar to Emacs Lisp string. You need a lot of backslash. There's only one way to do a string. So unlike Python, you can have triple quotes or whatever, or here doc in Perl, in PHP, in Ruby, or in PowerShell. You can quote them in several ways, so you don't need to have lots of this escape. But in Lisp, Emacs Lisp, and Common Lisp, and Wolfram language, you don't have that. So there's only one way to do a string, by this double quotation mark. And whatever, if you contain quotation mark inside, you need to escape it. So right now we are running into that issue. You need to escape, which is very nasty. But now something is wrong. Because you can see by the color, the coloring is not correct. That means something is getting screwed. Okay. Do I want to go through them? Nah, but anyway, so right now this whole thing is just a string. That's what you want to return. But what we want to do is that when this argument contains a circle or line, you want to turn them into a circle. Okay, so I'm starting to get into the direction of how to write this, but I haven't explained inversion yet. but I did explain that many times before. Okay, so let's go back. So let me just continue in the direction I'm going about writing this code in Wolfram language. Okay, so what we want right now is the SVG. Where is our SVG? There. Okay, so we go to SVG, go to the SVG basics. You want the syntax for a circle, so copy that. So in fact, actually, ignore all that shit. Ignore all that. Let's redo fresh. Okay, that's what we want. Okay, so make it one line, and now xahlee escape quotes. Now put a quote. Okay, that is what we want, but the coloring is still fucked. That is because my mod, I think my mod is not working properly, my xahlee Wolfram mod. But anyway, delete that. Actually, you need this kind of I'm smelling something burned. Okay, so let me double check, see if I got anything in the kitchen. Why on earth would it be exported as a path of lines instead of a primitive circle? There's a good reason for that. There's a solid there's a reason for that, because in practice, in fact, if you look at on the web, suppose you are God, you can look at all SVG files that exist on the web. They basically all are just using path. Okay, so that's a good question. For example, in SVG, you do have these different, primitives. Ellipse, you have also polygon. Here, you have several different type of primitives: circle, rectangle. But in practice, if you look at the real world, they are all just using not even a line. They are all just using path. Okay, so here, they are all just using path, because path is the most powerful. They generalize and kind of the most simple to deal with. I mean, in a sense, because you just deal with path. And path can also actually create a circle fairly complicated, because it can do the cubic spline and stuff. So basically, in practice, if you look at the web, all the SVG are just path, especially computer generated, like Illustrator application. They are all become path. Yeah, especially generated code. The reason is that because it's most general. You don't have to deal with all the special cases. For example, when you have a polygon, that's just a path of 4 points. And also for rectangle, also for line, you don't need a line, it's all path. But in the case of circle and rectangle, can you emulate by path itself? I don't remember. I think so. Okay, so we have to go check with the circle arc. Let's see what's the code. Yeah, path. Okay, so even a circle is just a path. So the path primitive is the most powerful. It generalizes, so it can represent everything. So that is why, in practice, every generated SVG, they are all just using path. Now, but the path is fairly complicated, because if you want to generate this circle, you can do it like that, or you can just have a path of 100 points. So anyway, the reason is that path is, it's just easy to deal with and in practice, and therefore in Wolfram language they don't bother to create a specialized output for circle. That's why. So the question is it a flaw? I mean, is that an imperfection? So if you are at Wolfram, and if you are responsible for writing the export function, the export function can export like literally hundreds file formats, if not thousands. Okay, so because they export SVG, scalable graphics format, but also any bitmap formats, such as JPEG, PNG, GIF, or GIF animation, or any video formats. There are like tens of video formats and tens of image formats, and there are three-dimensional CAD object formats, and there are tens of them. So the export actually this single function export all of them. So you can see, and also sound formats. There are like tens of sound formats over the years. So for example, here is all the sound format. So here is exporting Wolfram language graphics and sound, and this EPS, PDF, SVG, PICT format, WMF, Windows meta file format, TIFF, another image format, used to be popular in 90s, like huge, very rich format, TIFF, GIF, JPEG, PNG, BMP, that's Windows, PCX, that's like, I think that's Unix idiotic image format, XPM, yeah, that's X Windows, ASCII based text picture images, then AVI audio video, so that's about exporting the sound format, WAV, AU, SND, AIFF, then XDF, that's AutoCAD three-dimensional object format. Okay, so this export function export to basically effectively all format that ever existed, and either popular or standardized. Okay, export everything. So so you can look at, there's a document that lists all the possible formats. It shows somewhere. Okay, there it is. Okay, look at this variable export format, so you can see that. Okay, so we can evaluate it. That's a built-in constant. Any name that begin with a $sign, that means a built-in variable. Okay, so shift enter to evaluate it. So you got this bunch of, and copy the last output, and let's do postfix notation, and let's say length. So it exports 200 different formats. So so back to the question. So if you are, Wolfram research developer, you write this, nobody can write this. Actually, it takes different engineers because each of these format, TGF, TGA, TGF, TIFF, trig, they have a specification. And so it's not trivial. And it also export HTTP request, HTTP response. I'm not even sure what interesting. So each one of these format is very specialized, and they have usually a standard document specification. So it's not trivial to it's not likely one person do it all. So anyway, but if you are a developer at Wolfram, so one of the export format is SVG. So you need to. So the question is, when you have a circle in Wolfram language, do you want the SVG output to contain using the circle primitive. Now, basically, yes, you do. Okay, for example, in our simple case, because in this simple case, there's no reason, you don't want it to generate this stupid path with 100 points, right? But however, it can get very complex because the Wolfram circle, let's look at the documentation. The Wolfram circle, what? Oh, okay, so you need to do that. The Wolfram graphics primitive, which are different from SVG. So Wolfram graphics primitive, the circle, let's enlarge. The circle can also represent a Lisp, okay, and also a sector of it, okay. And then, so, Wolfram has its own tensor graphics primitives. So if you want to export circle to circle, then you need to deal with all the possible variations. So when it's a simple circle, yes, you can. It corresponds to a SVG circle, okay. But when you got a circle with a Lisp circle, then the SVG circle cannot do it. Let's see. So let's go back to SVG circle. So let's see, circle path basics. So the SVG circle can only represent a circle, but if you want a Lisp, you need to use the Lisp. Okay, so there are two different cases. Okay, but then if you want a sector, then the SVG circle cannot do neither of them. You need to use a path. Okay, that's the complexity. So you need to use a path for that circle. Okay, we got there. And that is just the that is just a circle primitive example. It gets very complex because then you got let's say you go to the list of all the graphics primitives. Let's say for two-dimensional graphics, because you also have three-dimensional graphics. Now, where can we click on that? Okay, let's open the graphics function. Then let's go to a page where it lists all graphics primitives. Okay, details and options. So you can have different triangles, arrows, B-spline curve, Bezier curve, circumsphere, disk field curve, and this graphics complex, which is a kind of complex and efficient format, array-based. Then you got infinite line. Then you got image, which is for bitmap images. So if you're gonna write a export graphics, just let's limit it to 2D case, to SVG. Then you gotta deal with all of these, so it becomes very non-trivial. And especially then you have color. You have color specification, arrowhead, different kind of arrowhead shape, and thickness, then dashing, what kind of dashing, and edge form, and so it becomes very complex. And then especially then you deal with hyperlink, event handlers, status area, style, button, tooltips, so that is why. Okay, so I believe that's why, because I have because I've actually written things like this before, exporting Wolfram language to another math graphics format gets very complex, because also similar situation is if you want to export something to HTML, let's say from org-mod, it becomes, the possibilities how you're gonna do it becomes very complex. Okay, that is why. That's kind of elaborate answer to the question why Wolfram language doesn't just export this circle plainly. Okay, I think I rambled too much. Then you have a question of how many people watching. Let's see, is it just like 1 people? 5. Okay. Well, the question about what is what's a inversion? The simplest. Okay, let me explain this. Okay, let me explain that. Okay, for the nth time. Let's go to inversion. There, geometric inversion. Okay, just let's think of the line. Okay, so this, forget about that circle. Just think of a plain line from 0 to 1. 0, 1, 2, 3. A line, array. So if you have a point P, okay, so let's suppose this circle here is radius 1. So here you have a point 1. So this O is 0. So 0 to 1, a segment. So you have a point on the line. So this point is, let's say, x. So if x is 1, then the inverse of x, that is 1 over x, is also 1, right? Now, if x is, let's say, 2, okay, so x is this p. So if x is 2, then what is 1 over 2? Well, that is 0.5. That is this q you see here, okay? So if x is 1, then 1 over 1 is still 1. If x is larger, is let's say x is 2, then 1 over 2, it becomes 0.5, okay? So if x is 3, then you have 1 over 3, which is 0.333, which is what this green dot position. So, but basically, the larger the x becomes, then 1 over x becomes very small, okay? So x becomes 10,000. So what is 1 over x? It's 1 over 10,000. So that's 0.0001, okay? So x can be a million, a billion, a petrabillion, a gigabillion, a billion of a billion. Then 1 over x is 0 point something something billion gigabillion 0. 1, okay? So that's the basic concept of arithmetic inversion, 1 over x. Dan, are you still here? So does that explain? I mean, you get what I mean by that, right? So if you are here, say hi. If you are still here, just make sense so people can see there's interaction. So that's arithmetic inversion, just 1 over x. Now, but what about geometric inversion? Basically, it's exactly just that, but you extend it to two-dimensional plane. So everything is just the same. So the inversion of P is this point Q, but now you can cover the entire plane. Okay, so but you can also just think of just like 1 over x, but now you can like rotate it. Okay, and you can define it. So how do you define it? How do you extend it to like a plane of 1 over x? Well, you can define it by, let's see if we can magnify this page. Yes, we can. So it's just any point. Let's see if we can. So any, what? Okay, so any point, let's see, can we, yeah, any point on the plane, we can find its inversion point Q. And the way you do that is for the given point P, the inversion point is such that OP, the distance from OP times the distance from OQ is equals to 1, which is the radius of the circle. Okay, so again, OP times OQ equals to 1. So when P is very large, very far away, OP is very large, then you need to time a very small number to become 1. And when P is very small, the OP distance is very small, then you need to time a very large number for their result to be 1. Exactly just like 1 over x. So, 1 over x is basically just like x times y equals to 1, right? So that's the idea for geometric inversion in a plane. And the same thing applies to 3-dimensional or 4-dimensional, okay? So that is the idea. Okay. Yeah, so that's geometric inversion, and this turns out this is my favorite concept in mathematics of all math. Some are more complicated, like manifold, topology. You have very complicated or algebraic geometry, or differential equations, or integrals, or derivatives. Of all the concepts in mathematics, or the complex number, or the Euler identity, I equals to pi, or the pi, the constant pi, and other constants. Of all the concepts in math, or fractals, like Mandelbrot said. But I think I feel that this inversion is my favorite idea of all math concepts. Okay, and it's kind of like also one of the fundamental idea, because inversion basically from algebraic point of view, inversion is basically from group theory point of view. So it's about multiplication and identity. Okay, multiplicative identity. Basically, you got two elements: x times y equals to 1. And what is that 1? 1 is like an object that represents identity. Okay, so inversion of a object is basically such that when you multiply together them, they become the identity. Okay, that's so that's kind of fundamental in that way. So this is multiplicative identity, which is typically represented by 1. There is, of course, another identity which is called additive identity, which is usually represented by 0. Okay, so that's basic algebraic concepts. So that is why 0 and 1, they are kind of the most important number in the entire mathematics. 0 and 1. You can think of them as numbers. Then you got 0, which means nothing. 1 is like one thing, the most basic one thing. So that's when you think of them as numbers. But however, in mathematics, they are not just numbers. They are like the whole entire algebra. So 0 is actually just an object that represents the arithmetic identity, and 1 is the multiplicative identity. So you got these two operations, multiplication and addition, and together they represent algebra. Groups and and vectors, algebraic fields, and all that. Okay, that's kind of like rambling some mathematics, which I know some, and but we are not going anywhere because because I want to write this code. I didn't finish writing it, nor did I do a good job like explaining Wolfram language, but I kind of went through. So it's kind of shit because this doesn't benefit me. I just wasted 1 hour rambling. you know, the more ideal is that either I explain something fundamental, like how do you write a function in Wolfram language, then how do you can, turn an expression into SVG, or either I can just code it, at least come out with a result I can show, but that's not the case. Okay, and then let's see what else. Then there's a bunch of other things I try to explain, where Wolfram language export to SVG. Yeah, we did that, but it's kind of esoteric. What else? I think that's it. Okay, so what I'm doing, this is kind of what I'm doing every day, working on them, but usually it takes like tremendous time just to explain what's going on. Yeah, I think that's it. Anything else? Okay, I think that's it. We went over actually, 70 minutes. Oh shit. What are all these? Oh shit. Okay. Bye guys. So today it's going over, it's fairly technical and obscure and stuff, but some pretty graphics. This one is the most beautiful. This is actually my, because this one involves my own creativity. You can kind of see the circular patterns hidden there. Okay, bye. Good night. Good night, Dan. Have a good day.